kicked off. Fantastic. Thank you, Jack.
Live on
14 according to the schedule. Yeah, soon to be live on the internet. So first off, our usual unconference meeting agenda. So if you have addenda to the meeting agenda.
Let's see, Dean had something he wanted me to add. Let me see if I can find it. Okay.
Hello, Zaki. Cool. So on the administrative updates front, ICS 5 is ready for review. Thanks, Anka. I guess not here for a few comments, which I've since addressed. That discusses port allocation. So the rename of module names to ports and some additional logic for allowing modules to bind to ports, and an explanation of how that would work with both sort of source authentication on the host state machine, like Ethereum, where contracts have addresses, and object capability authentication, like on Cosmos SDK or Agoric. So IBC will require that the host state machine supports one or the other, and this document explains like the slight differences in how the implementation will work. It should be pretty straightforward. I had a chat this morning with Vitalik and Justin Drake, one other person who left early from the call, with the Ethereum Foundation, who were interested in potentially using parts of the IBC spec for their inter-shard communication needs, which I think are mostly not yet standardized. They're focusing on the beacon chain and on the proof stake mechanism first. We call things maybe on some specific specs for packets and for channels, which they'll need something similar to. So I think Justin will join, maybe not these calls yet, but the ecosystem calls, maybe these calls in the future. And we'll see what we can share. We also discussed sharing some specs for light clients. They want to be able to run not only light clients for ETH2, but also light clients in WASM for other chains on shard chains on ETH2. And they were curious how much gas it costs to verify Tendermint headers in WASM. And I said I really didn't know. So,
what's the hash function used in the Tendermint protocol tree?
I also
SHA-2.
Thanks.
It's like SHA-2 truncated to 20 bytes, right?
No, it's the full thing now.
TM hash?
No, it's the full.
It's the full thing now. Okay, great.
Yeah.
Perfect.
We also discussed, the EF was also very interested in light clients using snarks, for which we would possibly want to switch to more snark-friendly functions, but that's a different discussion. SHA-2 is very snark unfriendly.
Yes.
I also wrote a blog post, as I believe Bucky had suggested, outlining the events of the IBC workshop, and referencing. I did link to Mark's presentation. Is that okay with you, Mark? The one that you put on YouTube?
Yes, absolutely. That's great.
Cool.
Yeah, the only qualification on the presentation is that it kind of begins in the middle of a conversation, so it's not just a presentation for somebody to get oriented from, but anybody who's already oriented and just wants more, it's fine.
Okay. Well, hopefully the first part of the blog post will provide a little bit of orientation for someone trying to figure out what was discussed. That's on a Google Doc at the link provided, so you're welcome to review it. I don't think it's been published yet. It's up to the person who runs the Cosmos blog, but it will probably be published today or tomorrow.
And there were two presentations. There was the relative routing, and there was the E-rights pegging. Did you do both?
That's right, and I have linked to both of them.
Okay, great.
Cool. Any questions on the administrative updates? Cool. All right, so maybe we'll talk about Dean's question first. So what are the next milestones? There is a very specific answer to that question because there is a literal milestone on GitHub. So if you go to github.com/cosmos/ICS, if my internet would load, the milestone number 2, which is also now pasted in chat, and I will link in the meeting notes. This consists of my understanding of all of the remaining items till we have IBC 1.0. By IBC 1.0, I'm denoting a version of the spec that we'll release. We'll call it 1.0. That will be the first thing that's implemented by June in Golang, which has already started, potentially by other people. Agoric, sounds like.
Yep.
And that we expect to be a standalone functional piece of software.
Cool.
So the remaining, go ahead.
Cool, thank you.
The remaining things to be done are, to my knowledge, listed on that milestone. If you think I've missed anything or think something shouldn't be on there, edit it. Specifically right now, I think finished ICS 5. I'm working on unordered channels and acknowledgements and have a few questions on those to discuss today. Apart from that, there's really not that much, except changing some of the data structures for multi-hop routing, which I have not yet done. And I think we should have rough arguments for why IBC provides exactly once delivery, just by saying that, proof by contradiction, this store key would have been written twice if the packet was delivered, that sort of thing, just written down.
Yeah, we had some more conversations this last week about the linear ordering versus the dependency graph, the full DAG kind of stuff. And Dean was additionally concerned about the overhead of the full DAG thing. And we were trying to think of some structure that lets you optimize for the case where you're mostly linear, but you have a couple of side branches, as opposed, there's sort of like fractal dimension 1 is where your dependency graph is just one big long line. Fractal dimension 2 is where every single commit could depend on some totally random commit or be totally independent. And the full DAG structure where every message mentions all of its dependencies and everybody is required to remember everything in the past just in case that shows up as a dependency is kind of necessary for the fractal dimension 2, but completely worst case for the linear case. So we weren't able to come up with a structure there, but we were sort of comparing it to the way that Git does its dependency tree versus Mercurial with named branches. And that's about as far as the discussion got. So we have some more work to do on that.
It's an interesting comparison, but I don't entirely understand what you mean. Aren't branch names just aliases?
I believe I haven't used Mercurial all that much. I believe at least in the earlier years of Mercurial, or maybe I'm thinking BZR, every commit kind of belonged to a single branch. And so that let you specify commit by saying branch name, comma, numerical index along the branch, but it didn't have the full-on general model that I'm familiar with from Git. And I think mercurial aliases are like that, but I think earlier mercurial branches maybe were like the BZR one. And it seems like the BZR thing has that approach where most of the time, most of your commits only have one parent, and merges and splitting off are special. And that might be sort of similar to our use cases for the message dependencies, where every once in a while you have a flow that, that deposit needs to happen before the withdrawal does, or before I reveal the thing to somebody that allows them to do a withdrawal. But most messages don't have an arbitrary number of dependencies. And so you want some structure that allows the recipient to have a low overhead way of keeping track of what they've received already, and not needing to remember all messages from the beginning of time.
I think maybe you ought to stick to BZR, because mercurial, at least the variant of mercurial that Google's been using recently, doesn't act the way you're describing.
Okay, it behaves more like Git.
Yeah.
Okay. Yeah. Okay. When I write that comparison, I'll go for the BZR analogy.
I feel like we could put a synchrony bound on ancestors, and just say that if you request ancestors too far in the past, like the packet's going to time out, especially.
Yeah, I floated that with Dean. I suggested that maybe every time you send a message, you also send, and by the way, here's another message ID that I will never ever cite as a dependency. The sender says, I've forgotten about this, and therefore the receiver is allowed to forget about it as well. And Dean frowned at that because it just sort of doubles the wire overhead. Yeah, Mark?
Yeah. The thing about ordering constraints that makes them very, very different than version control is, let's say you have, let's start with the linear with side branches. As the thing as the representation. So you've got a linear sequence, and we name the linear sequence, and we've got indices within other message outs, and the let's call it message M, and message M says, I must arrive after message 3 from the sequence, however it says that. So it says that somehow. And, but the receiver has already, is already long past processing message 3 in the sequence, because it's up to message 5000 in the sequence. Well, if the message M arrives after the message 5000, that's fine, because the meaning of the constraint is only what things what are the earlier things that this thing happens to be has to be after. So if all you know is a later thing that's also after, then if you're after that one, then you're still satisfying the original constraint. So it's it's just a very consistent with the general notion that when you've got partial ordering constraints, a full order that satisfies the partial order, you can always just collapse down to the full order if there's no other reason not to.
Yeah, it sounds like we may be able to amortize a lot, maybe half of that overhead, by providing message identifiers as a two-part, flow ID, comma, index within the flow. And if you're dependent upon flow X, index Y, and you've received flow X, index number greater than Y, then that constraint is satisfied without needing to remember anything more than a single integer Y for any given flow.
Yes.
And then we collapse the overhead down to how many flows do we have to remember? Is there some sort of explicit, I'm done with this flow, it's been merged into something else, I will never talk about this flow again, therefore you're allowed to forget that too. And sort of how much space can we save on the receiver side versus how many extra messages do we have to send to deallocate those flow identifiers?
Are these flows connected to channels?
It's conceivable. Like we might be able to have an extra benefit there that once the channel is shut down, then all the flows go away, and that we've shut down channels frequently enough that we can benefit from that. But I kind of think of channels as going to be longer lived between two different sibling modules on two different chains.
Well, the other question is whether flows ever cross channels. Markham, do you have a theory about what these flows mean?
So the only because collapsing partial orders into full orders satisfies the partial ordering constraint. And you can do that when you've got partial orders going over a single channel if the channel as a whole at the infrastructure level is naturally being delivered in some full order that's respected end to end. Then there's actually little reason to go out of your way to represent a partial order within the channel. Just let it collapse to the full order of the channel as a whole. And then the place where the partial ordering issues become crucial, which is the thing that that we went through, was the triangle property, which is when the ordering constraints are necessarily between different channels, where the triangle property example was where they're necessarily between different channels because they're going to different destinations. The other case where you can have something that where you don't want to collapse it into a full order is the one that Dean had brought up, which is you've got a full order with some delay, that's already accumulated an obligation to deliver a bunch of packets that haven't been delivered yet, and now you want to basically send a cancel signal through sort of a emergency traffic lane ahead of the backed up traffic. So that could just be a separate channel. So I'm not sure that these traffic lanes with the side constraints need to be something finer grained in the channel. If whatever the original partial order constraint is, if there's no emergency bypass issue, just let it collapse into the full order of a channel.
Yeah, I mean, I think the most interesting case is the cross-channel and probably cross-chain ordering of the triangle problem or of other sorts of complex multi-chain calls. In any case, that's IBC have lots of brainstorming. It does sound like if you were to branch off infrequently, that's a very use case specific thing. Like what trade-offs made sense will be dependent on the exact message patterns unless we can find an optimal way to do that sometimes and do the full DAG thing some other times. It seems like it's application specific.
Yep.
Cool. So speaking of efficiency things, I am implementing, or at least writing the spec for, unordered channels. And we basically, it doesn't require too much modification from the current thing. We basically have two options for how we will track received packets because we're no longer tracking a sequence number. So there are two ways to do it. We can store the packet data. There will still be an index. In some sense, it will still be a sequence number because we might as well increment it monotonically on the sending end, but it doesn't need to be received in order. So there will still be a packet index, and we could store a commitment to the packet data under a store key that's like the index plus the channel name. That's easy, and it works, and it doesn't require any extra accumulators, but it does come with a cost in state per packet that has to be kept around indefinitely, I think. because you don't want the receiving end to be, the sending end to be able to prove that it timed out. So if you delete it from state, the sending end could prove that it timed out.
If the sending end is sending them in a monotonic order, then you can save some space by keeping a number that all messages before this have been processed. Although I guess if somebody misses message 7, then you'll never be able to collapse out of that. So, yeah.
Yeah, that's right. You could still
I guess you could
keep an index
keep track
which
of
you've
some of
received
it,
all
yeah.
messages before. That's a good idea. That might actually help in a lot of cases. Let me just note that. Okay. The other thing we could do is store in state just a accumulator root, so like a Merkle tree root, and have basically tracked by the relayers and reconstructible from the transaction log a full Merkle tree of received packets. And then the timeout proofs would require a bit extra computation, a Merkle tree proof, but no, the amount of state stored would be constant. Do people have thoughts on that? I don't think it changes the data availability requirements in meaningful ways because we're already assuming that relayers can kind of scan transactions. So this is just addition.
Does that mean you have to send the whole proof every time you have to send? Yeah. Does that mean you have to send more data each time you publish a packet?
No, only when you're dealing with timeouts or receipts of failure. It's just used on the receiving chain to track which packets have been received. So when you receive a packet on the receiving chain, you would update the accumulator. Oh, I guess you would need to do some calculation to update the accumulator root. That's true. But you don't need to send that data in the packet itself.
And then it would be on the relayers to store those trees.
That's right.
Yeah, I'm not sure yet.
Okay. Neither is that. The second one is somewhat, certainly it's more complex for the relayers. They're about equivalent in terms of how hard it is to actually specify and implement it. It's not that hard, so we could test it or something. What do you think, June?
Would decrease the compatibility between the different worker proof formats we can change, because in before, say, the relayer only has to query the public endpoint, which is not depending on the worker commitment or any kind of commitment scheme. But now they have to run all the possible commitment scheme tree in their machine. That's one of the concerns.
I didn't quite understand that, June. Sorry. Can you summarize again?
Sure. If the relayer does not have to run the trees in their machine, then they just have to query the public endpoint of the chains. But now, if the trees are maintained in the relation machine, then for each different kind of commitment proof scheme, the implementation has to be served and run on the relayer's machine.
I see. Yes, that's right. It would make it harder to have light client relayers are still possible, but they would need to do more. They would need to track, like keep running filters on transactions, which they already do, but they would be more complex filters, and they would need to reconstruct parts of the Merkle tree.
And this might be independent from the actual, for example, the proof running on chain, because the proof scheme has to be like implemented separately so that it ultimately can be run by the relayer side, not the chain side. So it would increase the effort to implement.
So like in some cases,
relayers cannot run the commitment proof scheme just like as it was in the chain side. It has to be somehow, in some cases, re-implemented so it can be optimally run from the relayer side, let's say, which can be have a different environment or the constraints from the chain.
Yeah, I mean, the distinction between full node relayers and light client relayers is a little fuzzy. As long as light clients can verify state, they can offload the actual proof construction to the full nodes, but the full nodes have to be altruistic and willing to do it for them. And this requires that the full nodes track this extra state, which is not state.
Was that all you
arguably,
mentioned?
this is something. Go ahead.
Sorry, was that difference what you meant, June, by different environment? Just the difference between relayers and full nodes?
Or not being able to share the code between those two verifiers?
Yeah, not being able to share code between two.
Ah, okay.
Would a change like this impact, if I want to be a relayer and I start on a chain that's been running for a while, does it affect how far back I have to go, or how much extra work I have to do, or the likelihood of me being able to get enough data to populate the entire tree? It sounds like that'd be the
same Merkle tree forever, then you would need to fetch it. If it's refreshed occasionally after some timeouts, or when new channels are created, it would be less of a problem, but there would still be extra data to fetch. It is more complicated, I agree. There are more things we have to think about.
And I'm forgetting now the details of the timeout stuff. If the message gets acknowledged by the other end, do we get to remove it from the sender's tree, or are we committing to a data structure that grows without bound forever? Or is it
we do not have an acknowledgement of acknowledgements, because then the sender would have to write some other key, and then
that never converges.
You can never end that cycle.
Okay, but it's that if I want to produce a timeout proof, I have to crawl far enough backwards to find where the message was first posted, so I can prove that it was present.
That is right.
And I guess the metric I'm concerned about is, are we imposing an obligation on the relayers to accumulate data forever, or is that obligation only placed on somebody that wants to produce a timeout proof?
I mean, the relayers certainly, when they see that a packet has been received, no longer need to keep any data that might be used to generate a timeout proof. But they do need to keep. I mean, they need to keep some of the Merkle. It depends, on some of the specifics of the Merkle tree, like how much of it they would have to keep.
Is it kind of a pruning Merkle tree where, once these leaves are gone, then you can collapse, you can forget everything except their parent node, but you keep adding to the new one?
I think that would be possible, yeah. Maybe Merkle mountain ranges are useful here.
Yeah.
So with Merkle mountain ranges, you can keep ditching or keep summarizing old parts of the tree really efficiently without keeping the leaves.
But it does mean that if you start now and you, any new relayer coming online has to start by going back to the Genesis block and pulling out all of the packets coming back. I mean, every transaction going back to the very first one for that unit. Maybe it's per channel, maybe it's per something smaller than forever.
That's right. Or they have to request it from a full node. I mean, if they're a full node syncing from Genesis, it's the extra effort is negligible. But if they're a light client, they have to either do it, which is a lot of work for a light client, or they have to rely on an altruistic full node to provide it. Once the full node's provided it, they can verify it. So it doesn't impose any trust assumptions. But
that's a good point.
It is like, we don't really expect full nodes to serve all possible histories, right? So asking them to serve a lot of past transactions is also potentially expensive. Given this, I'm somewhat tempted to go with the simpler former option for now and try to do what you suggested, Chris, on also storing an index of like the greatest index such that we've received all packets before it for unordered channels. And in the optimistic case, that should work quite well. In the pessimistic case, we'll end up storing 1 hash per packet, which is not the end of the world. So, and it could be they could be deleted when the channels are deleted. So, cool. Is everyone on board with that? Zaki, Bucky.
Yeah, I think that makes sense. The simpler thing is probably better. I mean, I'm wondering if maybe this would be on the scope of this conversation, but there's been a few times now where this question has come up of like, oh, can we push more of the Merkle tree like off chain onto the relayers, etc. I wonder if there's like a general transformation that we'd be able to do further down the road as like an optimization if folks want that. You know, if there's a way we can still make those designs available later. Even though we go with like the simpler, more data on chain version for now.
Yeah, that's right. I mean, it's actually a problem that is way, way beyond the scope of IBC. We're just encountering it here because we're thinking so much about the details of what costs what. Like there's a bunch of state in like the Gaia state machine that is infrequently accessed and could instead be stored in a non-Merkle store and checked. Or like not stored in the Merkleized store that we store it in currently, and checked occasionally, which would like trade some compute for space usage.
Right. So yeah, it might be worth trying to review all of these, you know, further down the line. Maybe there's a generic way to address it or some kind of like transformation we can program once, but I'm just being maybe somewhat naive and romantic about it.
No, I don't think so. I think it should be generalizable. And interesting ways. I mean, and it may be the case that like relayers, if data availability and data storage ends up becoming a huge problem because there are billions and billions of packets being sent around, then certain relayers may only store subsets. Like one relayer will store, 10% of the channels. Another relayer will store another 10%. And that would work fine as long as they can be partitioned in ways that don't require like cross data availability things. So DAG ordering might pose more interesting problems there, but.
That for some purposes that actually makes sense. I think we're thinking of the role layers as mostly focusing on particular endpoints to particular channels, but that means that it's hard to find somebody with a global view in order to do global ordering.
Okay. Anything else on this topic, or shall we move on to acknowledgement data? All right, acknowledgement data. The issue here is 135. And there are a few outstanding questions. So we decided at the workshop that we wanted to have simple packet acknowledgements. such that the receiving chain can write some data when it executes a packet chosen by the application logic, and the sending chain can check that acknowledgement, such that if something went wrong, the receiving chain can write, failure, and the sending chain can notice that and do appropriate things. So this is separate from packet received. The packet will be received regardless. It's not a timeout. It's just saying that received and execution failed or resulted in some data. So basically my question here is whether we want, and I think of the same question, whether we want the IBC handler to be able to understand this return code at all, or whether it's just opaque. So the application on the receiving chain processes a packet, then it writes some data. And the data can be written to the Merkle store such that the sending chain can see that that data was written in correspondence with the execution of that packet. That's all easy. Just that alone doesn't require the IBC handler to understand any of the semantics of the data. It's just data, like packet data almost. It's just sort of a lightweight acknowledgement instead of sending a whole other packet back. So it's a bit cheaper. But if we want to do something like, for example, have ordered channels close on failure, then we would want at least a status bit, which is 0 or 1, to indicate success or failure. And the IBC handler will need to parse that, or the IBC relayer module will need to parse that to close the ordered channel whenever a failure is reported.
Does that mean that one side declaring that there was an error means that it thinks that the channel is closed and you don't end up, I thought the spec for doing a close was a multi-step handoff to make sure that both sides were in sync, and one side used this to close the channel without getting acknowledgement from the other side?
Well, that's the question, whether we want that ability. So, I mean, it's certainly true that IBC doesn't control the application logic anyway, so there's nothing preventing an application from receiving a packet it really doesn't like and just never accepting anymore. Basically the question is like, do we push part of that into the protocol and allow the application to say no, and don't send me any more packets, or require that the application separately call a closed channel and just stop receiving packets. So it's like a shortcut to close a channel, optionally.
That's a clear question. I don't have an answer on the I don't have an opinion on the answer.
Yeah. Another thing to just keep in mind with regard to the issue of acknowledgements in general, it doesn't bear to this on the particular question coming up. The particular question about closing, but the triangle ordering depends on the unacknowledged traffic from Alice to Carol being redundantly routed through Bob, or where Bob is able to ensure the data availability of the unacknowledged traffic. So the interesting thing there is just the reason it's specific to the unacknowledged traffic is, again, that anything that's already been delivered is ahead of anything that hasn't been delivered yet. So it's once again collapsing partial orders to full orders, but it's the unacknowledged traffic, which is the stuff that hasn't yet collapsed. And then signed, the equivalent of signed acknowledgements, the thing that would in a single machine system be a signed acknowledgement, the validated acknowledgement being the thing that caps the rerouted unacknowledged traffic, means that the acknowledgement itself caps the unacknowledged traffic. If there is no unacknowledged traffic, then you would still be routing through Bob the acknowledgement by itself as the sort of degenerate cap of the unacknowledged traffic.
So in the case of continued success, then recording acts may make a difference. But if either Alice or Carol declares that the channel is closed, then there aren't going to be any further answers, and it doesn't matter whether you ever get to the unreceived, unacknowledged traffic.
Yeah, if the channel being closed means that further sent messages on the channel will never be delivered, which is, I assume we all understand, we all agree that that's what we mean by closing a channel, then since those things will never be processed on the direct Alice to Carol line, they also do not need to be routed through the Alice to Bob to Carol line. They're dead traffic. So a closed channel is also a sort of terminal acknowledgement that means that there is no further unacknowledged traffic.
Yes. I agree with that. I think that's true in either case, right? We could have acknowledgements of failure, close the channel, or not, and it would still be the case that once the channel has been closed, it's treated as having, any in-flight packets having not been executed.
Yes.
I was thinking about what you said, Bob. We don't necessarily have to route that extra traffic through Bob. We just need to make sure that Bob can guarantee the availability of that traffic.
That's right. This was something that came up during the summit. As I kept talking about routing because my intuitions come from the days of single machines talking over connection-oriented protocols, and then Christopher, emphasized that in the world of chains talking to each other with relayers, it's really about data availability and who guarantees the data availability rather than about routing.
Yeah, and it's the relayer that's going to be providing the data anyway. So the best that Bob can do is observe that there is a proof that data is available to a relayer and hope that the relayer will deliver that extra data down to Carol at that time. So it may be that all that Alice has to do, Alice's obligations towards Bob are to put that data in a place where the relayer can find it. Maybe.
Yeah, a relayer that Bob relies on.
Yeah.
Yeah.
Mm-hmm.
It's a question of really, I think the way to think about it is it's handing over responsibility.
Yeah, it would be wonderful if there were some formal research in defining data availability very concretely. It always feels like a somewhat nebulous concept, which is hard to grasp. I really can't find, do you know, is there any academic research on data availability, Zaki? Like models of it, synchrony bounds? I can't, as far as I can find, it's almost entirely just discussed in the blockchain space.
It feels a little bit like a chain of custody question as well. Who has responsibility? From whom can you get it? Who's responsible for knowing this is the correct data?
Well, and the way Markham put it, if Bob isn't going to do the relaying and counts on Alice to make it available to Carol, and Alice thinks that she's made it available to a relayer, but it's the wrong relayer. I guess anything that Alice publishes, all of her relayers can see. But in order for Bob to count on it, he has to know that there's a relayer from Alice to Carol.
I think to get models of this, we need almost to talk about the process using IBC, or we have to assume some processes which are relayers. One of them might be the user, and assume that they have, which we can stipulate what data availability they have, like maybe one has access to one chain, the other has access to another chain. And if their data availability is partitioned across like disjoint, or at least partially disjoint subsets of the network, then decisions we make as to what data is available on which chain will matter, because it will be the case that like some relayer doesn't have access to chain A, so unless the data is available on chain B, if that relayer goes offline, then no relayer will have the access to relay it to chain C. Independently, whether we care about that case and whether it's actually likely is like different. But
and it also raises the question of to what extent are modules is on-code chain aware of relayers and aware of the identity of relayers? Or is that just some sort of external assumed service that happens in the background and we never have a name to which relayer is which?
Yeah, that's a good question.
So, a couple of things. One is, yeah, I'm fairly convinced that data availability represents like a giant blind spot of the distributed systems community for the last, 40 years. And like is basically unsystematized at this point. But like also like fundamentally important to public blockchains. So that was the first thing. The second is specifically on the relayer question. I think that I think that naming the relayers in the in IBC would probably be a pretty significant mistake. I think we want to model these things as like public databases in which like ad hoc participants can perform these roles.
At the very least, I'm sure that we want to allow new relayers to come on board without the permission or dependency upon the on-chain code being aware of them.
Yeah, I agree with that. But I think while we won't specify any details about relayer identities in the IBC protocol, except maybe as like having an address to which fees can be paid or something when we get to that point, I would think it fairly likely that applications may want, that have particular purposes may want to use specific relayers and be able to reason about them. At minimum, to restrict them, to say that my application works with this specific relayer, like who is me off-chain, and only I can relay my own packets. And that seems fine, but
I'm confused why. I'm not convinced that that's a good thing. That like being able assuming that like you might want to restrict who the relayer is would like improve the system.
Yeah, I think that the restriction that the only restriction that makes sense to me is in the other direction, which is, this is the only. I require this relayer be able to participate, but the thing about relayers is sort of an untrusting routing fabric. Is that all of anybody can redundantly try to relay, and that should only add value. It should never subtract value. As long as anyone succeeds at relaying, the packets get relayed. It doesn't matter who's doing the relaying.
Now, there's sort of a question of gas and spam attacks there, where before on-chain code takes the expense of doing the verification of what the relayer has said, you want to make sure that the relayer has some risk, has some way of some rate limiting there, or any given relayer is not allowed to submit too much traffic without some of it being judged correct and then getting repaid for it. But so that's kind of a question of, is the relayer paying for the processing that the chain is doing with it, or is the relayer handing responsibility off to the chain, and does it have enough at stake that it can't use that as an attack vector?
I thought the design mentioned that the relayers had to put up a bond that was forfeit if there. Is that right, Christopher, or not?
No, definitely not within the core protocol. I guess an implicit assumption is that the host state machines have some kind of execution pricing mechanism, i.e. gas. And whatever that execution pricing mechanism is already responsible for not wasting computation when fees weren't paid. So the relayer will have to pay a fee when they submit a transaction that will get deducted up front. So their account will get checked to see if they have enough balance. First, it will get deducted. Then, the transaction will actually be executed. Maybe they'll try to receive an IBC packet. And if it fails, and the relayer wasted some money. That's the relayer's problem. It's not really IBC's problem. And it's fine for the host state machine as long as proper gas mechanisms exists. Where I guess I could see this coming into play is on like very minimalist chains where you want lightweight IBC logic, and it's somewhat cheaper to either have the relayers have some bond or to use some like slightly more trusted relayers who are trusted at least not to spam. But I don't know if that's likely to be a huge use case. I certainly don't think we should build anything into the protocol for it. That's not what I'm suggesting.
Yeah.
So
I think we can just, sorry, Mark. Can I just finish what I was going to say?
Yeah.
I think it's like assume that there's an access control mechanism. That like anyone who's capable of performing the relayer function is able to access the resources of chains on both sides, but still not convinced that there's like a relayer identity piece.
Yeah, I think that it's interesting how parallel this is to the non-censorship of participation in chain validation, is that we want no barriers to entry for relaying. We want the ability to participate in relaying as long as you're paying your way, and then the gas versus bonding is sort of like, I mean, it's kind of like the proof of stake versus proof of work difference in open entry, where proof of work has full anonymity, and proof of stake requires bonds associated with some kind of identity. I'm not making a strong analogy here, but it's interesting that the underlying open entry lack of censorship principles apply to the job of relaying in an analogous way.
Yeah, although I think if we were to pick an analogy, I think the analogy would be physical cables. That's what the relayers are supposed to be. Physical data cables connecting the blockchains, where the blockchains are the machines. And like the more data cables there are between any two machines, the better, as long as they don't do too much, as long as you don't spend time receiving data on the data cable that you can't actually do anything with. And that's what the execution pricing.
Yeah, you want some coordinate. Ideally, there's some coordination so that any given message is only being delivered once. But on the other hand, you want to make sure you're not relying upon any one relayer, and you're not relying upon the relayer acting in good faith and simply not, saying, yep, I got this one, and then dropping it on the floor such that it never arrives. Yeah.
Okay, I want to quickly go back to the acknowledgement question so we can make a decision and I can write it this week. Do you have a specific use case for like ordered channels where timeouts would close them, and in that use case would failure also close the ordered channel?
I'm trying to remember the discussion that prompted this. Were we making more analogies to TCP?
The discussion that prompted the discussion of acknowledgements in the workshop, or
yeah, in the workshop is sort of automatically closing stuff. I'm not having strong feelings on this right now, but I'm trying to remember if somebody there did. If this was Dean that was talking about.
I think we were discussing the case when the receiving end was like was making write calls, and that it could receive a packet but fail a write call, and if that happened, you wanted to close the channel. I don't actually know what that would be analogous to in the blockchain context, but maybe there's something.
I mean, I guess it's if the receiving side can't make any progress because of some fatal error, and then you want the sending side to then be able to release the resources associated with the channel, which in our world might be, tokens that have been sequestered.
Yeah, I mean, that's possible regardless. The question here is more one of, do we want a minor optimization where setting a failure bit on an acknowledgement just closes the channel? And if there's not a strong reason to do it, I say no, just have the module close the channel. It's not that much extra effort. But
except if the other end, the far end, has decided that it's had an error and it's going to ignore the channel anymore, then there isn't a way to do the closing back and forth. You'll never get an acknowledgement from him that he's closed the channel.
I guess it depends on what level of the stack the close happens at. Is that IBC that's now responsible for acknowledging the close, or is that the application?
It would be IBC, or at least the IBC relayer module. I think the actual answer here might be that we should spend a little more time thinking about the closing handshake and what happens when it doesn't go the way we planned it to go, and do we deal with that case in sane ways?
Yeah, and that might tell us whether this extra bit would give us more functionality or correct functionality in more circumstances than the normal close handshake.
Sounds good. Let's do that then. I'll take a note. Cool. We are 2 minutes over. So thank you, everyone. And I will see you next week.
Sounds good. Thanks, everybody.
Sounds good.
Cheers.